Hello, friends. Welcome to Science Talk. I'm your host and resident oceanographer, Jim Asser. Now, this is from an abstract for a paper that's just been recently accepted for publication. So all I have available at the moment is the abstract. But this is a fascinating finding with what I consider to have some serious implications on matters. Hidden upwelling systems associated with major western boundary currents. Okay, what's going on here? All right, let's look at the abstract. Western boundary currents, WBCs, play an essential role in regulating global climate. In contrast to their widely examined horizontal motions, i.e., how the gyres form in the first place, less attention has been paid to vertical motion associated with western boundary currents. Here we examine vertical motions associated with the major western boundary currents by analyzing vertical velocity from 5 ocean synthesis products and 1 eddy resolving ocean simulation. These data reveal robust and intense subsurface upwelling, which are primarily along isopycnal surfaces in 5 major subtropical western boundary current systems. Isopycnal are basically lines of equal density. Like you have isotherms, isobars, right? That's all an isopycnal is, just lines of equal density. These upwelling systems are part of basin-scale overturning circulations and are likely driven by a meridional pressure gradient along the western boundary. Globally, the western boundary current upwelling contributes significantly to the vertical transport of water mass and ocean properties, and is an essential yet overlooked branch of the global ocean circulation. Ocean properties: temperature, salinity, nutrient concentration, heat content. In addition, the western boundary current upwelling intersects the oceanic euphotic and mixed layers, and thus likely plays an important role in ocean biological and chemical processes by transporting nutrients, carbon, and other traces vertically inside the ocean. This study calls for more research into the dynamics of the WBC upwelling and their role in ocean climate systems. Now let's look at the plain language summary. This study shows that intense upwelling systems exist along the major western boundary currents around the global ocean. In contrast to other well-known oceanic upwelling systems, for example, equatorial coastal upwelling, these western boundary current upwelling systems, which are essential branches of the global ocean circulation, have been largely unrecognized in the literature. This intense upwelling and the associated overturning circulation in the subtropical ocean basin can transport nutrients, carbon, heat inside the ocean, consequently act as an important yet unexplored route through which the oceanic biological, chemical, physical processes, and consequently the climate system, will be affected. This study calls for more research into the dynamics, etc. Okay, when they talk about subtropical, they're talking about basically around 30 degrees latitude, north and south. So what they're basically saying is, and I'm going to use the North Atlantic gyre as my example here, the Gulf Stream, because everyone's familiar with that. Now, if you really want to get into the details as to how oceanic gyres form and persist, as well as the upwelling, downwelling that occurs in the middle of gyres, as well as what Western intensification is all about, I refer you to my rotating systems video that I did some time ago. It is fairly comprehensive. If I was to go through that again, this would be a very lengthy video, when all you have to do is simply click on that video, and I'll include a video card in here so that you can do so and then watch that video. But basically, why do gyres form? Well, Earth is a rotating spheroid object. We have liquid sloshing around on the surface and down to depth as well. It's a water planet. And there's wind that happens. So you got wind blowing across the water, creating horizontal motion. Okay, it creates a pressure gradient. You have the rotation as well. So you have a wind stress. You have a pressure gradient. Water flows down the pressure gradient. You have Coriolis impacting matters, basically in a deflection, so that gyres form as a result of trying to balance the wind stress, the pressure gradient, the Coriolis, vorticity as well. So you have all these things trying to be in balance, and you get a gyro. Now, typically the gyres, because of Coriolis, water is being deflected to the right so that the water piles up in the middle, it domes up, and you, because of continuity argument, you create a downwelling in the middle. So it's a convergence zone, downwelling in the middle, and so water sinks and flows outward, and then the whole thing perpetuates. You get western intensification because the Earth happens to rotate in what? Sun comes up in the east, sets in the west. So it's an east to west motion, right? So you're basically, because of the inertia, the angular momentum, the water tends to pile up on the western side. So now you take the Gulf Stream, and the Gulf Stream is about 700, 800 meters deep on average. So what they're saying now is that you've got some upwelling. In addition to the gyra circulating around, there's a little bit of upwelling in along those intensified western boundary currents. On the eastern side of gyres, by the way, the if it spreads out, so it's not as deep and it really slows down. So the parameters, the physics involved, does not really promote an upwelling situation as it seems to be on the western side, where the currents are deeper, faster, and flowing at more intensity. So if you got this upwelling, okay, great. You could bring up nutrients, and that would be wonderful for productivity. Now, this is interesting to me because you've heard me say that as the oceans heat up, especially all that heat energy in the upper 5 to 700 meters, okay, that the oceans are going to really stratify, and that's going to impact deleteriously productivity. Basic productivity is going, if you set up a permanent stratification, we're not going to get the mixing of nutrients into the photic zone. Productivity is going to collapse, and right, and all bets are off, right? The ecosystem collapses. Well, this is interesting because if this is the case, then you could be bringing in some nutrients into the photic zone that may very well offset any loss of productivity due to the stratification. That remains to be seen, but that is the implication of what they're saying here. But here's another implication. All right, let's go back into the plain language. Right? What do they say? That actually was in the here we go. That it will transport nutrient, carbon, and heat. Well, I've discussed with you folks before that most of the oceanic heat is in the upper 5 to 700 meters. That sequestration is being reduced, if not to zero. Well, if you got this upwelling and it's bringing not just the nutrients and the carbon and the heat, does this facilitate the transfer of that latent heat energy back to the atmosphere? Does this facilitate, the outgassing of CO2 back to the atmosphere? That is something, there's an area of research that really needs to be done, because I can see that happening. I can see this being a situation where you hasten the re-input of heat and CO2 back into the atmosphere. And we know what that means. You increase the warming rate. So that That to me is so on several levels. Okay, the possibility that you might improve primary productivity and hence an ecosystem. Okay, great if that happens. But then the possibility of returning at a faster rate the heat and the CO2 back to the atmosphere. That's the troubling end of the thing. Now, again, I am speculating based on my knowledge of physics and oceanic processes that is something to consider, and studies are needed for that. So now to help you picture what's going on here with the isopycnals surface and so on, let me show you a couple little graphics here. And I'll start with, hang on, I'll start with this one. Hey, there we go. So here, if we look at this, this is the equator, 0. So this is 10 degrees south latitude, 20, 30, etc. 10 degrees north latitude, and so on and so forth. And what we see here is very intense stratification. As expected, you would expect to see very warm surface waters in the tropics to the subtropical, right? But the thing is, these are your isotherms. These are your isotherms. 6 degrees Celsius water in the tropics is a reasonable amount, reasonable value there. So these would be isotherms, but in the tropical waters, isotherms are basically also isopycnals. But you can see how they're pretty much parallel, how they're horizontal. Now notice that what happens as you start getting to the higher latitude, we start seeing the isopycnals, the isotherms, isopycnals, starting to go a little vertical, and they reach the surface. So you're going to start getting some mixing vertically. We see this shows similar things here. We see a little. This is very well mixed part of the ocean right here at about 40 degrees south latitude or so. So we see that again. We've got more of the. Let's see what are the values here. It looks like more isotherms, but again, we're seeing the horizontalness of it. That's what we're seeing. Yeah, theta C. Yeah, okay, so that's what we're seeing. Now, I want to show you this here. This shows very nicely, especially these darker black lines here, how the isopycnals, you can see right here, will bend go vertical right to the surface. So here we see a transition from horizontal, and it goes right to a vertical isopycnals going up to the surface. We see it even more so here. Look at this right here, right? So we can see how it bends towards the surface going vertical, and that facilitates upwelling. We've seen evidence of upwelling right here. That facilitates that because you remove the barrier, right? If you look at something like this here, right, these are barriers to mixing. But when you look at this here, well, now you're promoting vertical mixing. So now these last 3 slides I showed you were actual database. I'm going to show you conceptually what goes on here. These light blue lines are isopycnals. You see how it bends, goes vertical? And look, notice what they're showing here. Mixing. That's what they're showing. These little red squiggly lines, that's heat flux to the atmosphere. Heat is diffusing from the water to the atmosphere. This is why I say, well, will this hasten, increase the flux rate of heat diffusion to the atmosphere if you've got the situation going on western boundary currents? That's what's going on. So you got this mixing, vertical mixing, and you notice the mixing takes place where we have the isopycnals going vertical right to the surface. And then finally, I just want to show you this one here. This is the typical situation of most gyres, especially subtropical gyres, is that you have a counter, and again, this would be for the northern hemisphere. So you have a clockwise rotation that piles water up in the middle with an Ekman downwelling. Water downwells and then flows out this way to, looks like to upwell again. What we're seeing here is these sigma values, okay, that's salinity value. So we see the salinity values, which then could be, if the temperature staying the same, could be basically isopycnal values. And we see them going vertical. So along with whatever transport is happening, sub-mesoscale transport, etc. And if you have a counterclockwise spin, again, northern hemisphere, then you're going to have water pulled away from the center, and then you're going to have an Ekman upwelling in the middle. Whereas a good example of this is the gyre found in the Gulf of Alaska. You got a lot of upwelling, bringing nutrients. Oh yeah, Gulf of Alaska, very productive waters. So I just wanted to show you that, and again, more detail in my rotating video, rotating systems video. But this is what they were getting at when they're talking about the isopycnals. That's what they were getting at. So, this is very interesting for the reasons I outlined earlier. What does, perhaps this will help with productivity, but what does it mean for heat and CO2 diffusion flux rates back to the atmosphere? So, hope you found this interesting. Thank you for your time. We'll talk soon. Hello, folks. This is Jim here with Science Talk, asking you to please subscribe to my channel and to inform others of my channel and of the work that I do. Please share to social media platforms that you use. Also, as a reminder, don't forget to click the bell so that you know when I load up more videos. Finally, I ask that you support the work that I do by becoming a patron at patreon.com. Details in the description box below. Thank you for your support.